Hello. In this video, we're going to take a look at Newton's laws of gravity by taking a look at example problems number 3 and 4. Gravity is such an interesting concept because it's a non-contact force. All that you need are masses near one another, and you have a force of gravity. In our world, we don't typically recognize it because the mass of the Earth is so large that we don't recognize our force of attraction to any other mass but the Earth. But in example problem number 3, we're just looking at 3 masses that are laying near one another, and we want to look at the gravitational force between each one of those. Specifically, we want to take a look at the gravitational force of the 20 kilogram mass, which is this mass right here. So we're not worried about the force of gravity between the two 10 kilogram masses, only worried about the force of gravity of the 20. So even though you have a diagram right here on the picture, I'm going to do most of my work on the whiteboard, but what we're going to see here is we assume there's some symmetry, right? So there's 5 meters, 20 meters between center and center, in between each. And what we recognize is the force of gravity between the 20 and this 10 is going to be an attractive force, right? So that's going to be a force of gravity there. I'm just going to number each one of these so that I can subscript all of my forces. 1, 2, and 3. So I'm going to call this force 2, 3, and see that it's acting up and to the right. At the same time, the 20 kilogram mass is going to be attracted to the other 10 kilogram mass in this direction. And we're going to call that force 1, 2. We notice that these forces should be exactly the same because we have the same masses with the same distances. So right away, we should recognize that the magnitude of force 1, 2 is equal to the magnitude of force 2, 3. Their directions are going to be different, but the magnitudes of those two forces are the same. Because the force of gravity and the equation to calculate the force of gravity, magnitude, we'll just call that F, is equal to capital G M1, M2, all over the distance between them squared, right? So we're going to need to find the distance between these masses. And that distance is from center to center. So we need this entire distance here, right? We're going to call that our R. That distance should be the same for both forces, okay? So we see a triangle being made right here. If we take a look at each one of these. So when we're looking at R, we can right away recognize, okay, we're going to need these distances, right? So our R is this distance right here. What we do know is this is 5 centimeters and this is 20 centimeters. So right away, using the Pythagorean theorem, we can say this is the right angle, right? That R is the hypotenuse of that triangle. So R is going to be the square root of 5 centimeters squared plus 20 centimeters squared. So plugging that into our calculators, we get R to be 20.6 centimeters. Remember that we want all units in meters, so that's going to be 0.206 meters. That gives us our R. What may also be important when we're looking at our vectors is this angle, theta. So I'm going to go ahead and solve for that angle, theta, as well. And if I look at my triangle, I would say I'm going to use my known values, not a value that I calculated. So I'm going to use the tangent function. And tangent is going to be opposite, which would be the 5 centimeters, divided by the adjacent side, 20 centimeters. So 5 divided by 20 gives us 1/4. Theta is going to be the inverse tangent of 0.25. And we will find that theta, the angle theta between there, is equal to 14. Right over here as I'm writing out 14.04 degrees. Okay. So now these are going to be important values that we're going to want to use to find our vectors. So that's just some of the geometry. That's just some of the thought as I read the problem, some information that I'm going to need to know. Okay, so now let's go ahead and begin to solve the problem using our whiteboard here. I'm going to redraw the 20 kilogram mass, right? So this is our 20 kilogram. What we know about the 20 kilogram mass are the forces that are on it. We're just only looking at the force of attraction between these 3 and 1, 2. Okay. We're ignoring the force of gravity of its weight. So we're going to ignore the force of gravity of the Earth on this, and we're only looking at these. So right away I can see, remember when we have forces at an angle, we break up into components. So this is force 1, 2, x, and this is going to be force 1, 2, y. At the same time, I'm going to have this force 2, 3, x, and I'm going to have force 2, 3, y. So if I redraw my free body diagram with only forces going in the x and y direction, I notice right away we have 2 in the x components, right? 2, 3, x. We have force 2, 3, y. And over here we have force 1, 2, x and force 1, 2, y. Since, and we can break up into components, right? So again, looking at our geometry. Looking at our x and y directions. This angle theta is what I calculated. So that's the same as this angle on this side. So be careful what angles you use to determine your x and y components, right? So that's our angle theta, the way that I drew my angles for the vectors in this case. So what I would say here is looking for f(1,2), I would use the sine function. The sine of theta is the opposite side. So f(1,2) sine theta. At the same time, for the y component, it's the adjacent side. So that's going to go with the cosine function. Cosine theta. So f(1,2) cosine theta is equal to f(1,2) y. So again, you're just going through a routine of solving things that you can solve for. We're going to set up our components. So looking at this direction, we're going to have, again, sine theta is equal to the opposite side, f(2,3x) divided by f(2,3). f(2,3) sine theta is equal to f(2,3x). The cosine function will go with the y component, equal to f(2,3y) divided by f(2,3). f(2,3) cosine theta is equal to f(2,3y). So what we can conclude here is because f(1,2) equals f(2,3), because they are the same masses and same distances, right? So their values of the force should be the same. These two are equal. If those two are equal, that means the x components are equal, and those two will cancel out. So the net force that is here is simply going to be, so the force on the 20 is going to equal F F12y plus F23y. Right, so we're just going to add those two up. So we know they're in the vertical, right? So what we need to find is what is F12 and what's F13. So knowing the equation for the force of gravity is equal to G mass 1 mass 2 all over the distance between them squared. So again, the reason we know they're equal is because F12 magnitude, right, is going to equal G mass 1 mass, because why am I saying 1, 2? It's 1, 2, and 3, right? Oh my goodness. This should be 3 the whole way through. Just realized that I numbered that with a 3. All right, forgive me. If I go back to my picture, I numbered that a 3, so really we're looking at F13 is the number that we should be using there. So I apologize. We'll go back and change all that. This is 1, 3, 2, 1, 3, 1, 3, and so on. Right, so 1 and 3. And that's important simply because this is the generic equation here. So we want mass 1, mass 3, the distance between 1 and 3 squared. Right, the magnitude of force 2, 3 is going to equal G mass 2 mass 3 and the distance between 2, 3 squared. So again, since mass 1 and mass 3 are equal to each other and the R values are equal, these are also equal, right? So they're equal to one another. So I'm just going to solve it one time. Don't need to put it in my calculators more than that. So the magnitude of the force 1, 2 equals the magnitude of the force 2, 3 equals G, which is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times mass 1 or mass 2, both of which are 10 kilograms, times mass 3, which is 20 kilograms, divided by the distance between them squared. So remember, you don't use the 5 or the 20. It's the straight line distance from center of gravity to center of gravity, which is our R value. We found to be 0.206. So we're going to divide that by 0.206 meters squared. So your meters squared cancel, right? That cancels because you're going to square that as well. Kilograms cancel with each of those. We end up with units of newtons, and the value of our magnitude of the force 1, 2, which is equal force 2, 3, is equal to 3.14 times 10 to the minus 7 newtons. So that's the magnitude. That means force 2, 3, y equals force 1, 3, y, magnitude, right, in the same direction, equals F 2, 3 cosine theta. It'll be the magnitude of F 2, 3. So combining these, so that's equal to 3.14 times 10 to the minus 7 newtons cosine 14.04 degrees. That'll give us our magnitude of that. For that, I get 3.046 times 10 to the minus 7 newtons. So that's the value of each of the components, right? So that's each of the components. I come back up to my picture and I realize, okay, that just means I'm going to add them in twice, right? So using this equation, the net force on the 20 kilogram is the y components added together. So my net force on the 20 is equal to 3.067 newtons J hat plus 3.046 times 10 to the minus 7 J hat. Since they are going into the same direction, that's simply going to be Q times 3.046 times 10 to the minus 7 newtons in the J hat direction. So the final answer is that the force on the 20 is 6.092 times 10 to the minus 7 newtons in the J hat direction, or 90 degrees. So again, recognizing that the two forces are going to be equal to one another, that the x components cancel, you only have the y components to the forces. Finding that y component using SOHCAHTOA, adding those together, both in the y direction, gives us our final force on the 20. Okay, let's continue with this with number 4. On number 4, we're going to use the force of gravity to create an orbit, which again, that's the amazing thing about gravity. You do not need contact between the two masses. There is just this force. In an orbit, that force of gravity is used as the centripetal force necessary to keep something in circular motion. So here we have a small moon orbiting around the planet in a circular orbit at a speed of 5 kilometers per second. It takes 23 hours to complete one full orbit. What is the mass of the planet? Right? So as we take a look at that, drawing a quick picture, right? So I'm going back to our good problem-solving skills. Looking at number 3. Sorry, number 4. Right? Quick picture. We have the planet, right? Here's our planet, and here's our moon. Label them like that. And they're traveling around one another, right, in an orbit. What you know is that there's a force effect on each of them. It is equal, simply opposite in direction, right? So since it's moving in circular motion, what that tells us is that the force of gravity is the center-seeking force right? The centripetal force needed to keep it in motion. Okay, that's going to be needed to keep it in motion. So what else do we know? Right. So what we're looking for here, we're given the speed. So that speed of 5 kilometers per second. So immediately I need to change that to meters per second. So 1,000 meters is 1 kilometer. That's how I would change that. So we look at that as 5,000 meters per second. I also know the value of our G, gravitational constant, 6.67 times 10 to the minus 7 newtons. Let's call the mass of the moon. Don't know what that is. Let's just call it M. Let's call the mass of the planet a capital M because we know it's bigger. But we don't know the mass of either one of those. We also know that it took 23 hours to complete one full orbit. So this is the time for one cycle. Remember that takes on a different name in circular motion. That is period. Period is the time it takes to make one cycle. So it's hours per cycle, right? Again, we're going to change that to seconds. There are 3,600 seconds in 1 hour. The period of this revolution is 82,800 seconds. Okay. All right, so that's everything that we know given the problem, right? So now we got to start thinking through this. Well, if I need the mass, again, it's going around in this circle, right? It's going to have the force of gravity on it. That's going to equal our centripetal force to allow it to go in a circle. That's the only force acting on it. So the summation of forces towards the center equals mass times centripetal acceleration. So that means your force of gravity is the only thing acting towards the center is going to equal your mass times your centripetal acceleration. So the force of gravity is equal to m. Centripetal acceleration is v squared over r. So there's my m, right, that comes into play. That would be, this is the moon's orbit, right? So we're going to keep that as a lowercase m. This is the moon. What I'm looking for is this one. What is the mass of the planet, right? So the planet's not moving, it's the moon that is moving around the planet. Again, relative motion, but that's how we're going to take a look at it. Here, then, the force of gravity, we can say is G, mass of the moon, mass of the planet, divided by the distance between them squared, equals mv squared over r. So here, the mass of the moon actually cancels out. It's on both sides. We don't need it. One of the radiuses cancel out, but we still need it. It's still showing up. So if I want to solve for my m, we get here that G, capital M over R is equal to V squared. So I do know V and I know G. I'm solving for M. So rearranging to solve for M, we get M equals V squared R divided by G. So I'm going to need R. How could I find R from what information I know? So we have not used this, right? But we do have the velocity. Remember, in circular motion, the velocity is the circumference of the circle that you covered per time, right? So we have to recall that in circular motion, speed is 2 pi r over the period. So since I was given the period and the speed, I can actually use this equation to solve for r, because I know the period and I know speed. So rearranging this equation, period times my speed is equal to r, both sides my time. I get r to be period times my velocity divided by 2 pi r. So 82,800 seconds times the speed of 5,000 divided by 2 pi gives me my radius of this orbit. So that comes out to be 5.7 meters. Now I can use that up here to solve for my mass of the planet. V squared, 5,000 meters per second squared, times my R, 6.59 times 10 to the 7th meters, all over G, 6.67 times 10 to the minus 11 Newton meter squared per kilograms. squared. So the kilograms flip to the tops, your 2 meters cancel out. Remember that a Newton is a kilogram meter per second squared. So the kilogram cancels out one of those. The seconds cancel. You should end up with units of kilograms. So your mass turns out to be 2.4. Don't forget to square that speed. 47 times 10 to the 25th kilograms. Okay. Real quick, I'm going to work through those units. So we have meters per second that gets squared, right? Multiplied by a meter. So right away we can say, okay, that takes out one of those. So what we're left with on the top is a meter over second. On the bottom, we have a Newton times meters squared per kilogram squared. So remember, when you divide by a fraction, you reciprocate. So that's equal to meters over seconds times kilogram squared all over Newton times meter squared. So that meter cancels, right? And we get kilograms squared all over seconds times newtons times meters. Well, a Newton is a kilogram meter per second squared, right? So we get kilograms squared. I think I'm missing something here. This second should still be squared, right? Because we just crossed out one of those. That should stay squared. There we go. So we get kilograms squared all over seconds squared. A Newton is a kilogram meter per second squared times a meter. All right, that needs to stay on the bottom, right? Ending up with an extra meter here. 1 kilogram cancels. We end up with kilograms over meters squared. So what do we do there? Let's see. So we should end up with a kilogram. So that was on the top, right? Times a meters. Because we had V squared times R. Got rid of one of those, left the meter second squared all over units of G Newton meter squared per kilograms squared. Newton meter squared per kilogram squared. Flip that up. Makes me wonder our G value. All right, I think the mistake is up here. That doesn't cancel, that should be meters cubed. So let's start this all over again. Looking at our units, you're gonna have, right, we have meters on the top per second that gets squared times meters. So that's gonna give us meters cubed per second squared on the top. Then we're going to divide by newtons times meters squared over kilograms squared. So that's going to give us meters cubed over seconds squared times kilograms squared over newtons times meters squared. A Newton, right? So then you get meters cubed over seconds squared times kilogram squared all over kilogram meters per second squared, which is a Newton, times meters squared. And flipping that gives you meters cubed over seconds squared times kilogram squared times seconds squared all over kilograms times meters times meter squared. There we go. So the meters cubed cancel with those. 1 kilogram cancels, seconds squared cancels. You end up with units of kilograms. So my mistake back here, I don't know why I canceled those. All right, give you an idea of dimensional analysis there. So again, in circular motion, remember that you need a force acting towards the center to keep it in circular motion. We call the combination of all forces acting towards the center the centripetal forces needed to keep an object in circular motion. So that's where this equation came from here. All right, that's Newton's laws of gravity. Please practice these problems over and over again to understand why we made all the choices we made in our equations.